Hello everyone, Adhokshaj Mishra this side, and today in this session we will be talking about art of anti-debugging, as in we will talk about how anti-debugging is implemented, various ways to do it, and various uses where it can be used for something. So this is my brief introduction. Currently I am working as a malware security researcher in optics, focusing on Linux and container side of things. In malware I focus on offensive as well as defensive side, as in I try to figure out new attack vectors as well as try to figure out how to detect and possibly prevent those attack vectors. Apart from that, I am a Linux and open source enthusiast. I love presenting in various security related meetups and conferences across the globe, and you can get in touch with me on the LinkedIn with this username. So this is today's agenda. We will start from basics of anti-debugging and their uses. Then we will cover some techniques in detail to detect debuggers, to detect certain artifacts which are created when a process is trying to debug another process. And then we will see some demonstrations, some source codes of their actual implementation. So at very basic level, anti-debugging is just a bunch of techniques which are used to detect and sometimes prevent debuggers and related analysis tools. For example, there are tracing utilities like ltrace, strace, and then there are sandboxes like Cuckoo which rely on such tracing tools. So if we engage in anti-debugging, many times we are also able to detect and possibly prevent a large chunk of tools by same set of techniques. And most common uses apart from malware for this anti-debugging has always been anti-piracy things, mostly to prevent someone from blatantly copying your software without paying you. Then we move to detecting debuggers, and then there are many techniques. So the easiest one to implement is something called timing analysis. So the basic idea is that if a program is running outside debugger, it will run fast, and if someone is trying to debug it, someone is trying to inspect what exactly is going on, it will take time. So if we measure time between runs and then we compare it with some known threshold, then maybe we can say that okay, if it takes something more than this amount of time, then probably someone is trying to analyze what we are doing. But then this is not really a very reliable method, because time taken to run the same code differs on same machine from run to run, and if we are comparing across different types of hardware with different configuration, then it changes from one machine to another machine rather drastically. And if we are moving to certain slow hardware, for example some very old CPU or rather constrained machine, then timing analysis basically fails to work properly. So this is not really a reliable method. Now for implementation, we can simply take timestamp before doing our critical work, where we want to monitor whether we are being analyzed or not, and then we can take the timestamp after doing it, and then we simply take the difference and then we compare with some known value. And this known value is generally taken by some trial and error or some sort of repeated measurement, and then taking a safe boundary. So this way we can say that okay, probably someone is trying to analyze our code. So for demo, this particular technique is really easy to see how to implement it. For example, we can look at this particular code. So this is where we are doing our stuff. So this is a tight loop where we are going to measure this, And what we are doing here, that we are taking timestamp before this inner loop, then we are doing something in repeated loops until we detect that this duration has gone with more than with some known duration. Then we say that okay, maybe someone is trying to analyze our process under some sort of debugger. Now if you want to see how exactly it works, we can probably try setting a breakpoint somewhere inside this inner for loop, we can then try to see whatever is going on there, and then we continue this program, and then this will basically fail. So that looks something really simple. We can run this tool and this will just simply go on and on and on. So for debugging, what we can do, that we can do this. We can attach to this process, we can check at entry point, we can come here, we start here, and then we can probably check the source code where to stop exactly. Now what we can do, we can probably set a breakpoint at line number 24, and then we continue. Then maybe we can continue and continue bunch of times, and we simply remove all the breakpoints and continue. And now it says that debugging attempt has been detected, and it has taken this much time instead of whatever threshold we have set in our code, and this process has terminated. So this is one way to detect this. Now another method is that is also commonly seen in various malware samples, is that they try to go through the list of all the processes which are running, or maybe they run some sort of heuristic to figure out if there is a debugger that is attaching to their process or has already attached to their process as a debugger, and then they try to match it with some known utilities or something like that. So for example, if we do not want to see if certain process has attached to us, we can simply iterate through all the processes, and then we can compare them with known analysis tools, and if some such tools are running, we can simply exit the code or probably change behavior. Or if our code is started from inside a debugger, generally the debugger process will be somewhere in parent process chain from our own process. So we can start from own PID, then we can check who is our parent, then who is its own parent, and so on, and somewhere in the chain that debugger process will be there. So and for Linux, the common method to figure out if some other process is attached has attached to our own process as a debugger, the simple method is to read this /proc /self/stat file, and the fourth entry is the PID of process which is trying to debug our own process. Or we can try to figure out whichever process is our own parent process, and then we can try to match them with known tools. For example, I am trying to match them here with GDB and LLDB servers, that is debugger from LLVM, and then we can simply check for those paths. And this method is really simple to for full implementation actually. So if we go here, okay, here is the code, detect process. This is how we are detecting here. We read this proc self stat process, and then we try to see which process is attached to our own process. So if we run this, for example, we can go back to this one and we do this. Simply it says that I am not being debugged, and if we do this and run it, it says I am being debugged because it sees that GDB is in its parent process chain. So this is yet another method. Then we can try to figure out if there are certain artifacts which are generally created when a debugger is trying to debug a process. We can probably check for them. So most common method that you can probably find on internet on way too many blogs is called basically attaching to ptrace. So basically you use the ptrace is called to attach to your own process as a debugger. And the thing is that only one process is allowed to attach to a process at any given time, as in no two different processes can attach to same target process at same time. So if this particular call fails, that means that some other process has already attached to our own process. So we can do this very simple check here, but the problem with this is that an analyst can probably hook this ptrace call and change its result. So even though we are being debugged, we will not be able to detect it. So this is where this particular technique fails. Then there is a slightly better method from this, and what we do that instead of doing the ptrace once, we repeat the ptrace bunch of times, and since we know that we are doing it, we can obviously check for expected values. So then at each check we can probably maintain some sort of internal state. For example, here I am maintaining a variable, and then after some modifications, some mutations, I can try to check if my internal state is in expected way. For example, if here I am modifying this variable offset, and for first call I am just setting it to 2, for second call I am multiplying it by 3. So after everything has gone successfully, it should be 2 into 3, as in 6. Otherwise there is something else going on. Now this relies upon the fact that the malware analyst is going to hook ptrace blindly and is going to return the same result. So our first condition will still work because ptrace is hooked, but second condition will fail because here we are expecting this ptrace call to fail, but somehow it is still getting succeeded. So this particular modification will not happen. So this relies upon the fact that an analyst will probably not pay attention to figure out that ptrace is being used at multiple places and some sort of internal state is being maintained. But then there are ways to circumvent this as well, again by tracking how many times ptrace has already been called or from where it is being called, or maybe trying to overwrite that monitor state from somewhere else, something like that. So finally we move to one more technique which relies on invalid system call, but before that we will go through demonstrations of these two. So demo for first one, this code is simply only this much. There is only one ptrace call, there is nothing else going on here. And for second one, it is just a little bit bigger. We are doing the same thing as I demonstrated in the slides, just maintaining a variable and then doing some modifications and checking for expected value. So if we run this ptrace one, it says normal execution, and if I do this inside debugger, it says don't trace me. So basically it is detecting. Similarly, if I run this ptrace true after outside debugger, it runs normally, but if I run it inside debugger, and then again it says don't trace me, because both conditions are not getting satisfied. Only second one is getting satisfied, but not the first one. So this is also working here. And now we move to our next technique, which is relying upon invalid system calls. So here what we are going to do, that instead of using a valid system call, we are going to use an invalid one, as in something that doesn't really exist. So what happens that if we try to execute that, program will simply crash outside debugger. But what we are going to do, that we are going to attach ptrace and wait for that error to happen, then intercept it, then fix this whole thing inside memory and continue execution. So for this example, what I have done, that I have defined this custom syscall which doesn't really exist, and then I have defined a function saying print custom, which simply calls that particular syscall. Now this is where I call that print custom function inside a loop, and here in the loop what I am doing, that I am attaching to myself, and then I am raising a signal to continue. So this basically ensures that the process which is monitoring this part of code gains control whenever something goes wrong here. And then in tracer, what we are going to do, that we are going to monitor this part of code, and we are going to monitor for this particular syscall to trigger, and then we will fix that syscall so it executes correctly. So how we are going to do that, that we are okay, so what we do, that we take the process ID of the process which is running this particular code, and then we wait for that process to change status, and then when the process has changed status and it has stopped, we basically set ptrace options that it will terminate the process on exit. And then what we do, that we configure ptrace again to stop at syscall execution. So what happens here, that whenever a syscall is triggered, as in whenever this particular function is called, this will simply stop and give the control back to us. So what we do, that we copy all the registers, and then we check that which syscall is getting called. And here we are checking that if our own custom syscall is getting called, then we do something else, and that something else is basically this. We are putting the correct syscall number, and we are setting up its parameters, and then we are overwriting registers for child PID, and then we are asking it to resume execution. So this is a rather convoluted process, yes, and this is not really trivial to implement, but the plus side is that it is also rather difficult to figure out properly, or to analyze it properly if you don't know that something like that is going on. And now we will see the demo for this one. So this is how this whole code looks like, and here what we are doing, that in the beginning we are forking the process, as in this will create a copy of its own process, and then we check that if we are in child process, we run this this part of code. This is the code where we are trying to use our invalid system call. And if we are in parent process, then what we do, that we take the child PID, and we run this tracer process where all that ptrace stuff is going on to intercept the syscall, compare to figure out that it is calling our custom syscall, and then we simply are overwriting it with correct syscall number and setting the parameters properly, and then we are simply executing it. So if we run it, it looks something like this. Okay, it says that try attaching debugger to child process. Now here is something to do, and this is something slightly difficult. So for example, if I do this and I run it like this, like we were running first two samples, so we see that okay, nothing happens. It runs exactly as in the previous case, but the thing is that here instead of attaching to the child process, we attach to parent process. So child process ran completely outside debugger, so nothing really happened. So what we need to do that we need to ask our debugger to attach to child process instead of parent. So we do this and then we run it again, and now it simply crashes because it is not really going to work. And if we try to see what exactly went wrong, yes, it says something went wrong at ptrace.cpp line 21, and then something failed somewhere deep down inside the libc. So this is the intended behavior for that particular code. If you are trying to debug it, it is going to fail because nothing is going to fix its illegal system call or its parameters. Now then we move to our next artifacts, and that is breakpoint. Breakpoint is something, for example, when you attach to a process, you may want to stop at certain location in code. So breakpoint is a mechanism that debuggers provide, using which you say that okay, whenever the program reaches here, just stop, and I want to see whatever is stored in memory or registers or whatever instructions are going to be executed, something like that. So generally there are two types of breakpoints. One is called software breakpoint, one is called hardware breakpoint. So software breakpoint is generally implemented by overwriting first byte with 0xCC, which is machine code for software interrupt int03. Now we can put a breakpoint by saying by writing full machine code for this instruction, which is 2 bytes, but since there is single byte version available, so generally we go with this one. Most of the debuggers are going to use 0xCC. Then to detect breakpoint, what we can do that we can to try to see if 0xCC is present at first byte of all the instructions that we want to monitor. So but this particular technique works only when that analyst is going to set a breakpoint, otherwise it is not going to work. So generally it is not really used in isolation. It is used in combination with some other techniques that we have already covered. So the most common or we can say the most easy method is to we can take a pointer where our function is starting, and then we can probably take a list of offsets to instructions. So basically we have the first address, and then we have offsets or indexes where our all the instructions are stored, and then we simply loop over them and try to compare their first byte with 0xCC. If 0xCC is found, we can say that it is the breakpoint is set, otherwise we can say that breakpoint is not set. Now there, as I already told you, that there is another variant of this one for same this particular interrupt, and the 2-byte variant is basically 0xCD0x03. So this is actually for setting up interrupt. For 0xCD is for interrupt part, and 0x03 is for this interrupt number. So whatever interrupt number we are going to use, we can put that particular number after that 0xCD part. This particular case is given special privilege by Intel. So most of the debuggers go with this because at places we may be dealing with single byte instructions, for example 0x90, which is basically an op. So in that case, setting up a 2-byte breakpoint is not really a good idea. So 0xCC is what pretty much everyone is using. But in case something is trying to set up 2-byte breakpoint, we can check for first 2 bytes, just like we did for first byte in this previous loop. And for demo part, so there are 2 ways. For example, if in first case we are checking for breakpoint at only first instruction and not anywhere else, assuming that whoever going to analyze our code is going to stop right at the beginning. So this is most trivial case. Or in a better way, what we are doing here, that we have a list of offsets, and then we figure out where our this secret function is located in memory at runtime by typecasting a pointer, and then we pass all this detail to this particular function where we are simply iterating over offsets and comparing the first byte. So if we run this detect breakpoint, it says try breakpoint at secret. So we try to run it under debugger, detect breakpoint 2, and then we simply set a breakpoint somewhere at secret, and then we try to run it, and it says breakpoint detected. So just I so we have covered a bunch of techniques for this anti-debugging things, starting from timing analysis to process check to detecting for various artifacts, and we can extend the same method to detect potential cases for patching. The method will be basically same. We will run this same loop, but instead of checking for this particular byte, we need to either have a duplicate copy of all the code that we want to check, or maybe we can hash the part of code that we want to check at runtime, and then we can compare it with some known good hash, or maybe we can use that hash as a key for some other part of code. So there are other possibilities. If you have any questions, you can probably send me on LinkedIn. This whole presentation deck and all the source code that I demonstrated, or whatever is present in the slides, will also be shared with you by the conference organizers. Thank you.